Hello friends, welcome to my lecture on joint probability distribution. This is the third and final lecture on joint probability distribution. First we define functions of random variable. Let x and y, xy be a random variable with probability function r density fxy and the cumulative distribution function fxy, and let gxy be any continuous function which is defined for all xy and is not a constant. Then z equal to gxy is a random variable 2. Okay. For example, if we roll 2 dice, if x is the number that the first die turns up, whereas y is the number that the second die turns up, then z equal to x plus y is the sum of these two numbers. In the case of a discrete random variable xy, we may obtain the probability function fz of z equal to gxy by summing all fxy for which gxy equals to the value of z considered. Okay. That is, fz equal to probability that z takes the value z will be equal to double sigma fxy, where gxy is equal to z. That is, sum of the values of x and y becomes equal to z. We will take the sum over all those values of x and those values of y, where the sum of x and y values give you z. Okay. The distribution function of z will be fz equal to p z less than or equal to z, where we will sum over all those x y, where the sum of the values of x and y are, where the gxy not necessarily the sum of x and y. In the example we have taken gxy as x plus y, but it is arbitrary here. So, gxy must be less than or equal to z. So, if in the case of the probability function fz, we will take the sum over all those values for all those pairs of values of xy such that gxy equal to z. In the case of cumulative distribution function fz, we shall take the sum over all those values of fxy where the pair of values of xy satisfy gxy less than or equal to z. Okay. So, where we sum over all values of fxy where gxy is less than or equal to z. Now, functions of random variable, if you consider here continuous random variable xy. Okay, we earlier discussed discrete case. Now, let us consider the case of continuous random variable xy. So, we similarly have fz equal to probability that z is less than or equal to z. We integrate over all those values of xy which satisfy the inequality gxy less than or equal to z. Okay. So, fxy dx dy. So, where for each z we integrate over the region gxy less than or equal to z in the xy plane. Okay. And when you take the probability, okay, the probability here, then we will take a small fz will be, we will integrate over all those xy for which gxy equal to z. Okay. So, the number egxy, okay, we have defined this is discrete case. In the case of continuous random variable, we have the distribution function fz. Now, we have to consider the expectation of gxy. The number expectation of gxy equal to sigma over x, sigma over y, gxy, fxy, when xy is a discrete probability distribution, and when in gxy is a continuous joint continuous distribution, we have integral over minus infinity to infinity, integral over minus infinity to infinity, gxy, fxy, dx dy. This is called the mathematical expectation or expectation of gxy. We assume here that the double series in the discrete case converges absolutely, and the integrals here, okay, over the xy plane, okay, exists. Integral of mod of gxy into fxy over the xy plane exists. Okay. So, it can be shown that expectation of agxy plus bhxy equal to a times egxy plus bhxy. Okay. An important special case here you can take as expectation of ax, a you can take 1, b equal to 1, and gxy as x, hxy as y. So, you can say expectation of x plus y equal to expectation of x plus expectation of y. Now, we know that the conditional probability, of an event A given event B is given by this formula. Okay. Probability that A given B is equal to probability of A intersection B divided by probability of B. So, if PV is not equal to 0. Now, suppose that A and B are the events x equal to x and y equal to y, where x and y are discrete random variables, okay, having the joint probability mass function f x y. Then we have probability that x takes the value x, y takes the value y, equal to probability that x takes the value x, y takes the value y divided by probability of that y takes the value y. And then now probability that x takes the value x, y takes the value y is f x y, and probability that y takes the value y is the marginal distribution function of y with respect to the joint distribution, okay, provided that the marginal distribution function or marginal density of y with respect to the joint distribution is not 0. So, this is the marginal distribution of y. Now, let us denote the conditional probability y f x given by x given by, okay. So, this can be denoted by f x given by x given by to indicate that x is a variable and y is fixed, okay. So, we have the following definition: if x y is a two dimensional discrete random variable with joint probability mass function f, and if f x f y are the marginal distribution functions of x and y, then the conditional probability of x given by equal to y is denoted by f x given by x given by, and is defined as f x given by x given by equal to f x y over f y y. F y y is the marginal density of marginal density of y with respect to the joint distribution. So, for each x within the range of x. Similarly, conditional distribution of y given x equal to x is denoted by f y given x, y given x, and is defined as f y given x, y given x equal to f x y over marginal distribution of x with respect to the joint distribution for each y in the range of y, okay. Here we assume that marginal densities f x x and f y y are not 0. Now, since f x given by equal to f x y over f y y, f x y is 0 greater than or equal to 0, f y y is also greater than or equal to 0. This is density function, this is marginal density. So, they are both non-negative, and therefore, their quotient is non-negative. This is valid for all x y in their range, and sigma f x given by is equal to sigma over x f x y. When you keep y fixed and sum over all when you keep y equal to y, when you keep y fixed and sum over all the values of x, okay, then you are getting f y y, okay. So, f y y divided by f y y equal to 1, okay, and that is this follows from the definition of marginal distribution. And so, what happens is that the conditional distribution, okay, f x given by is a probability function. This is a probability function. Similarly, we can show that f y given x is also a probability function. There we will, if you want to show this, then you sum over all by such that f by over x equal to sigma over by f x y divided by f x x we will have, okay. Now, here we are summing over all by x is fixed, so we get f x x divided by f x x, which is equal to 1. So, both the conditional distributions of are probability functions, okay. This is conditional probability function of x given by equal to y, this is conditional probability function of y given x equal to x. Now, if x and y are independent and they are discrete random variables, independent discrete random variables, then we know that f x y equal to f x x into f y y for all values of x y within their range, okay. So, now f x given by equal to f x y over f y y, by definition, okay. This is by definition, and if x and y are independent, by definition f x y equal to f x x into f y y. So, let us put it here, what we get f x x. So, if x and y are discrete random variables and they are independent, okay, then the conditional distribution of x given by equal to y is equal to marginal distribution of x with respect to the joint distribution. Similarly, f by over x equal to f x over by over f x x is equal to f by y. Okay. So, if x and y are independent discrete random variables, then the conditional distribution of x given given by equal to y is equal to marginal distribution of x with respect to joint distribution, and conditional distribution of y given x equal to x is marginal distribution of y. So, the converse is also true. If f x over by x given by equal to f x x for all values of x and y within range, then f x y is equal to f x x into f y y. How it will follow? Let us see. F x y equal to see by definition f x given by x given by equal to f x y over f y y. Okay. So, we can say or f x y equal to f x given by into f y y. Okay. Now, f x given by x given by equal to f x x. Okay. So, f x x equal to f x x into f y y, and therefore, x and y are independent random variables. Okay. Similarly, if f y over x by given x equal to f y y, then f x y equal to f y given x by given x f x x equal to f y y into f x x. So, that x and y are independent random variables. Now, we can similarly define the conditional distribution for two dimensional continuous random variables by replacing probability distributions with probability density functions. So, if x and x y is a two dimensional continuous random variable with joint probability density function f, and if f x and f y are the marginal density function of x given y equal to y, then f x given by x over by x given by equal to is defined as f x given by x given by equal to f x by over f y y, where f y y is not equal to 0 and x belongs to the interval minus infinity to infinity. The conditional density function of y given x equal to x similarly is defined as f y given x equal to f x y over f x x, where f x x is not equal to 0 and x belongs to the interval minus infinity to y belongs to the interval minus infinity to infinity. Again, f x given by x given by equal to f x y over f by y is greater than or equal to 0 for all x y belonging to R square, and integral over minus infinity to infinity f x given by dx equal to integral over minus infinity to infinity f x by dx, and this is independent of x. So, f y y, and we get this integral as f y y. So, f y y over y f y y is equal to 1. So, from the definition of marginal density function, we find that this value is equal to 1. So, f x given by is a probability density function. Similarly, we can show that f y given x is a probability density function. If x and y are independent continuous random variables, then we have f x y equal to f x given x f x x into f y y for all value of x y belonging to R square, and then f x given by by definition is f x y over f y y, but f x y equal to f x x into f y y. So, when you put it here, you get f x given by equal to marginal density function of x with respect to the joint distribution, and f by given x equal to f x y over f x x, okay, which is f x x into f y y over f x x. So, this is f y y. Okay. So, we have the same result, okay, like in the discrete case. The converse is also true. If f x given by equal to f x x for all L values of x y belonging to R square, then f x y equal to f x given by f y y. This follows from the definition of conditional distribution, and this is equal to f x x. So, we get f x x into f y y, and then x and y are independent random variables. And similarly, we can see for f y given x if it is equal to f y y, then f x y equal to f y y into f x x, and so x and y are independent random variables. Now, let us consider a problem. on marginal and conditional probability distributions. So, the joint probability mass function of x y is given by p x y equal to k times 2x plus 3y, x equal to 0 1 2, y equal to 1 2 3. Let us find first the joint probability distribution. Okay. So, x varies from 0 1 2 and y varies from 0 1 2. So, let us say here we have x, here we have y, and x varies from 0 to 2. Okay. So, when x is 0, y is 0, okay, p 0 0 equal to 0. When x is 0, y is 1, okay, we have 3k. When x is 0 and y is equal to 2, we have 6k. When x is 1, y is 0, we have 2k. When x is 1, okay, y is equal to 1, so we get 3 plus 2, 5k. Okay. And when x is 1, y is 2, so 3 2 is 6, 6 plus 2, 8k. And when x is 2, we have 4 here, y is equal to 0, okay, so we have 4k. When x is 2, we have 4 here, y is equal to 1, so we have 7k. And when x is 2, we have 4 here, y is equal to 2, so we have 6 here, 6 plus 4, 10k. Okay. So, 6k plus 3k, 9k here we have, 8 plus 5, 13, 13 plus 2, 15k, and we have 10 plus 7, 17 plus 4, 21k. Let us check again. When x is 0, y is 0, we have p x y 0. When x is 0, okay, y is equal to 1, we have 3k. When x is 0, y is equal to 2, we have 6k. When x is equal to 1, we have here 2, okay. So, y is 0, so we have 2k. When x is 1, we have 2 here, here we have 1, we have 3 plus 2, 5k. When x is 1, y is 2, we have 3 2 are 6 plus 2, so 8k. When x is equal to 2, we have 4 here, y is 0, so 4k. When x is 2, y is 1, we have 7k. When x is 2, y is 2, we have 3 2 are 6 plus 4, 10k. Okay. So, this is 15 plus 9, 24, 24 plus 21, 45k. Okay. All right. Let us see the sum of the columns. Okay. So, here what is happening, we are getting fxx, because when you sum along the row, okay, you get the value of fxx, because you are summing fxy, sigma fxy, you are summing along the row. So, y varies from 0 to 2. Okay. So, this gives you fxx. Okay. So, now fyy. So, this is 6k, this is 7 plus 5 12 plus 3 15k, and this is 10 plus 8 18 plus 6 24k. So, 24 plus 15 39 plus 6 45k. So, 45k is the total. Okay. Now, this is 45k. Okay. So, 45k must be equal to 1. Okay. And this means that k is equal to 1 by 45. Sigma fxx, okay, when x varies from 0 to 2 is equal to 1. Okay. So, this implies 45k equal to 1. So, k equal to 1 by 45. Okay. Now, we find the marginal probability function, marginal distribution of x. So, let us form the table of marginal distribution function of x. So, x fxx. So, x takes the value 0 1 2. Okay. So, when x is equal to 0, we have fxx equal to 9k, that is 9 by 45. Okay, when x is equal to 1, we have 15k, 15 by 45, and when x is equal to 2, we have 21k, so 21 by 45. Okay, and we have similarly marginal density function of y. So 0, 1, 2. F by y. So when y is equal to 0, y is equal to 0. Okay, we have 6k. Okay, so 6 by 45. Okay, when we have y equal to 1, it is 15 by 45, and when y equal to 2, it is 24 by 45. Okay, so this is the marginal density function of y, this is marginal density function of x. Now let us find conditional probability distributions. Okay, so conditional probability distributions means we have to find f x y, f x given by x given by. Okay, this will be equal to f x by divided by f by y. Okay, f x by divided by f by y. So f x given by x over by okay, so f by y, f x y is equal to k times 2x plus 3y. So we have f x given by x given by equal to k times 2x plus 3y f by y. Okay, f by y is equal to 6 by 45, 15 by 45, 24 by 45. Okay, so we have to do it for y equal to 1, 2, 3. Okay, y equal to 0, 1, 2, 0, 1, 2 and so on. So f x, so we have to first find f x given by x by equal to 0. Okay, by equal to 0. Okay, so by equal to 0 means we have k times 2x. Okay, 2x by equal to 0 means f by y is 6 over 45. Okay, so this is equal to 45 by 6 into k into 2x. Okay, so 45 by 6 into the k, 45k equal to 1. So we have 1 by 6 into 2x. Okay, 1 by 6 into 2x, that is x by 3. X by 3. Okay, and similarly we have to do it for y equal to 1, y equal to 2. Okay, so we have to do it for y equal to 1, y equal to 2. So f x given by x over by x given by. Okay, we have to do it for this f x by over f by y. Okay, let us take y equal to 1 now. Okay, so f x given by okay, we have found for y equal to 0, for y equal to 1 we have to find. So f x 1, okay, f by 1. Okay, f x 1 is equal to k times 2x plus 3, k times 2x plus 3 divided by 15 by 45, k times 2x plus 3 divided by k times 2x plus 3 divided by 15 by 45. Okay, so 15 by 45 means 1 by 3. Okay, so 3k into 2x plus 3. Okay, so 3 by 45, k is 1 by 45. So 3 by 45 into 2x plus 3. Okay, so we have 1 by 15, 2x plus 3. Okay, and then f x given by for y equal to 2. Okay, So, this is for y equal to 1, and we have earlier found for y equal to 0, for y equal to 2. Okay. So, f x 2 f by 2, okay. This is equal to k times 2x plus 6, k times 2x plus 6 divided by 24 by 45. Okay. So, this is 45k into 2x plus 6 divided by 24. Okay. 45k equal to 1. So, we have 2x plus 6 divided by 24. Okay. So, we have x plus 3 divided by 8. Okay. So, f x given by x given by, okay, for y equal to 0 we found to be x by 3. Okay. For y equal to 1 we found it to be 2x plus 3 by 15, and for y equal to 2 we found it to be x plus 3 by 8. Okay. Similarly, we can find f by over x, by f by given x by given x. Okay. For x equal to 0, for x equal to 1, for x equal to 2. Okay. Let us find f by given x by given x for x equal to 0. So, we have f 0 by divided by f x 0. Okay. So, f 0 y will be equal to sorry, p 0 y, you can say p 0 y equal to x is 0. So, 3 k y, okay, 3 k y divided by f x 0 is equal to 9 by 45. Okay. Now, what this is 45 by 9 into 3k by, okay, 45k equal to 1, 3 by 9 is 1 by 3. So, it is y by 3. Okay. F, so y equal to x equal to 0 we have found. Okay. X equal to 1 if you want. So, f by given x will be equal to f, instead of f actually we have taken p. Okay. So, let us write p. So, p 1 by divided by f x 1. So, how much p 1 by will be? P 1 by will be equal to k times 2 plus 3 y divided by 15 by 45. Okay. So, this will be equal to you can say this will be equal to 45k equal to 1. So, 2 plus 3 y divided by 15. So, f by given x equal to 2 plus 3 y divided by 15 when y equal to 2. Okay. And f by given x can similarly be found for y equal to x equal to 2. Okay. X equal to 2. So, p 2 y divided by f x 2, this is equal to k times 2x plus 3 y we had. So, 4 plus 3 y divided by f x 2 we found to be equal to 24 by 45. Okay. So, this is 45k will be equal to 1. So, 4 plus 3 y divided by 24. Okay. So, f by given x we find for x equal to 0 to be by y 3, for x equal to 1 we found it to be equal to for x equal to 0 it was by over 3, for x equal to 1 it was so 2 plus 3 y by 15. Okay. and when I take x equal to 2, why I wrote y equal to 2 there, okay, this is for x equal to 1. For x equal to 2 we got 2 be 4 plus 3y by 24. Okay. So, this is how we find the conditional distributions of x given by and by given x. Okay. Now, suppose we have the random variables x and y whose joint probability density function is f x y equal to x into by e to the power minus half x square plus y square, x greater than 0, y greater than 0 and 0 otherwise. Okay. So, when in the first quadrant f x y is given by x y into e to the power minus half x into x square plus y square. So, marginal probability density function of x let us find first. Okay. That is, we want to find f x x. Okay. So, f x x will be integral over minus infinity to infinity, okay, f x y dy. Okay. So, we will have it over first quadrant only. Okay. X is greater than 0, y greater than 0. So, we have to integrate over in that. So, with respect to y. Okay. So, integral over the first quadrant. Okay. So, we are integrating, when we integrate we here keep x as fixed. Okay. Probability that x equal to x we want, y varies. Okay. So, we take a vertical strip. For the vertical strip in the region x is fixed, okay, y varies from 0 to infinity. So, 0 to infinity x into y e to the power minus half x square plus y square dy. Okay. So, x times e to the power minus half x square we can write outside. Okay. X times e to the power minus half x square we can write outside, integral 0 to infinity y times e to the power minus half y square we can integrate. Okay. So, let us make the substitution, half y square equal to, let us say, t, then we get y dy equal to dt. So, we get here limits remain the same, we get x e to the power minus half x square e to the power minus t dt, which comes out to be, this integral comes out to be 1. Okay. So, we have x e to the power minus half x square where x is greater than 0. Okay. And so, f x x equal to x e to the power minus half x square when x is greater than 0 and 0 otherwise. Okay. So, f x x equal to x e to the power minus half x square when x is greater than 0 and 0 otherwise. Okay. Then marginal PDF of y, marginal PDF density function of y similarly we can find. Okay. So, marginal density function of y we can find to be f by y equal to integral over minus infinity to infinity f x y. We are integrating, yeah, we are integrating in this first quadrant. Okay. Because there only f x y is non-zero. So, we are taking now y fixed. Okay. Y fixed means we have to take a horizontal strip. Okay. So, horizontal strip we have to take in the region like this. So, we have to take okay. So, this is for we are taking y fixed. Okay. So, this is will be equal to integral over 0 to infinity x y e to the power minus half x square plus y square dx. Okay. So, by e to the power minus half y square we shall write outside and integral 0 to infinity x e to the power minus half x square dx. This we have just now seen, this comes out to be 1. So, this is by into e to the power minus half y square and this is valid when y is greater than 0. This equal to f x f by y is equal to this when y is greater than 0. Thus, f by y is equal to by e to the power minus half y square when y is greater than 0 and 0 otherwise. Okay. Now, conditional PDF, okay, of x given by equal to y. So, we have to find this. Okay. conditional PDF given by equal to y. Okay, conditional PDF of x given by equal to y. So, this means that we want the let us go to the definition conditional. Okay. So, we defined the conditional distribution of x given by equal to y. Okay. If x y is a two dimensional discrete random variable, this is for the case where f x y over f y y. In the case of continuous, we have f x over by x over by f x by y y over y. Okay. So, we come to this one. Okay. So, conditional probability of x given by equal to y is f x y, okay, given by equal to y. Given by equal to y means f y y. Okay. So, this will be equal to x by e to the power minus half x square plus y square divided by f y y, that is f y y we have found just now, by times e to the power minus half y square. Okay. So, this comes out to be x e to the power minus half x square. Okay. X e to the power minus half x square, which is nothing but, you can see this is equal to f x x. Okay. So, we can see here that f x y is equal to f x x into f y y. Okay. And therefore, x and y are independent random variables. Okay. So, it answers this question also. We have found the conditional probability distribution of x given by equal to y, it came out to be f x x. Okay. It came out to be f f x. So, f x x, so it turns out that f x y equal to f x x into f y y, and therefore, x and y are independent. Okay. So, then we have these theorems which are important ones. The mean or expectation of a sum of random variables equals the sum of the means, that is expected value of x 1 plus x 2 and so on, x n is expected value of x 1 plus expected value of x 2 and so on, expected value of x n. And then the mean and of the product of independent random variables, suppose x 1 x 2 x n are independent random variables, then expectation of their product is product of their expectations, and then variance of the sum of independent random variables equals the sum of the variances of those random variables. So, that is all in this lecture. Thank you very much for your attention.